Auzubillahiminash-shaytanir-rajim. Bismillahir-rahmanir-rahim. This is the lecture number 10. Actually, it's a part of lecture number 9, because in previous lecture we have discussed electron microscopy, and in this lecture we will also continue that, the electron microscopy. So this is just like an overview of the previous lecture, or the slideshow of the previous lectures. I'm going through it just in overview. So our new lectures start from here. So this is actually the second part of the lecture. So in this lecture we will basically discuss the different parts of the scanning electron microscope and transmission electron microscope, its objective and its performance. The first thing is that we need to discuss the basic component of scanning electron microscope. The scanning electron microscope basically consists of three bigger parts. One is the electron optics, that is used for the focusing of electrons and the creation of electron. The other is the sample and sample holder, and the third one is transducers, or the detectors used to detect the electron and move the data to final photographic plates, or to the results to get the information or images or pictures. So the electron optics, we need to know the condenser lens. These are actually the lens to focus the electron beams on the objective lens. The other part of the electron optics are the objective lens. Objective lens are responsible for the size of electron beam impinging on sample surface, and the third part of the electron optics is the electromagnetic coils, and these electromagnetic coils are responsible for driving the raster scanning by deflecting the electron beam. In case of sample and sample holder part, we need to know the size of the samples, that is the size is that is in the centimeters, and the rotation of the sample. We can rotate the sample along 3 dimension x, y, z to get images from all directions, and the conductivity is required for samples to be measured. For non-conducting sample like biological specimen, metallic coating is required. The third part of the scanning electron microscopes are transducers, and transducers are also called as a detector. In the detector section we have scintillation device, that is a sample made from a dope glass or plastic target that emits a cascade of visible photons when struck by electrons. And the other detector is the semiconductor transducer, that is actually create electron hole pair when it is struck by electrons, and thus it increase the conductivity. This is actually an image showing the process, or the working process of the scanning electron microscope. We have this scanning electron microscope, and in this the electrons are produced in the electron gun, which is also called as an electron source. These electrons are accelerated along a particular direction with the help of electric field, and further it is directed with the help of electric and magnetic fields. These are the actually the condenser lens, and the condenser lens are used to concentrate this electron or focus the electron on the objective lens. This electron finally fall on the sample, and then it can get the information from this, we can get the information from the backscatter electron and create the image from that backscatter electron informations. Basically, when electron strike the sample surface, that different type of processes occur, and different type of electrons are emitted, or X-rays are emitted, and this electron interaction of the electron with the sample is a very complicated process, and this backscatter electron can get information about the sample topography, composition, and some other properties just like electrical conductivity. So There are different types of backscatter electrons. Just like some of the electron are called as a secondary electron, the backscatter electrons, and characteristic X-ray. Light is also produced, that is called as cathodoluminescence, and specimen current and transmitted electrons. The first part is the secondary electrons. The secondary electrons are actually produced when the primary electron, that is actually the electron produced in the electron gun, that struck the surface of the samples. The electron generated as ionization product, and it is called as secondary electron because it is generated by the other radiations. The other radiations are actually the primary radiation that are produced due to the electron gun. So this radiation can be in the form of ions, electrons, or photon with sufficiently high energy exceeding the ionization potential. And these secondary electrons detectors are common in all SEM. SEM is secondary electron imaging, or SEI, can produce very high resolution image of a sample surface revealing details less than 1 nanometer in size. The other electrons that are produced due to the collision of the primary electron with the surface of the samples are the beam of electron that are reflected from the sample by elastic scattering. So these backscatter electrons are often used in analytical SEMs along with the spectra made from the characteristic X-ray. Because the intensity of AC signals is strongly related to the atomic number of the specimen, BC images can provide information about the distribution of different elements in the sample. So we can also get information from the backscatter electrons, and there are different detectors used to collect information or to detect the backscatter electron that is present at different position. And the third part, or the third process that occurs due to the collision of primary electron with the samples, are the characteristic X-ray. These are actually the emitted, these characteristic X-ray are basically emitted when the electron beam removes an inner shell electron from the sample, causing a high energy electron to fill the shell and release energy. So these characteristic X-ray are used to identify the composition and measure the abundance of elements in the sample. So these are actually some of the images from scanning electron microscopes. These are actually nano ZNO nanobelts and ZNS nanobelts, that is converted through chemical reaction. So this is actually a very nice morphology, and the resolution is around 400 nanometers, and this work is published in the Annual Review of Physical Chemistry. So if we elaborate the advantages and disadvantages of scanning electron microscope, then in case of in advantages part, we know that this SEM can pursue different type of samples, maybe conducting or non-conducting, and so based on the surface interaction, no requirement of electron transparent sample is needed. And the other advantage of SEM is that it can take the images from all the directions through XYZ, because we can easily rotate the sample by the rotator in the scanning electron microscope. It has some disadvantages as well, that is the demerits. The first disadvantage is low resolution, because it can only scan the surface, and usually is about a few tens of nanometer. And the other is that usually it requires surface strain coating with metal for electron conducting. So we can move towards transmission electron microscopy. This is an image of the first transmission electron microscope that has been introduced in 1933, and is already present, originally present at IG Faberwaki at now, and is displayed in a museum in Munich in Germany. So transmission electron microscopy is basically a technique where a beam of electron are passed, or it is transmitted through a sample. The size of the sample is ultra thin because we need to pass the electron through it, and this transmitted electron can get information from the interior of the sample. From this transmitted electron we can get the image, and this image is further magnified and focused onto an imaging devices, such as the fluorescent screen or a layer of the photographic film, and then it's further detected by CCD camera. So this is the history of first transmission electron microscope that has been introduced by Max Kroll and Hans Raska in 1933 and has been commercialized in 1939. So this is also again a Hitachi transmission electron microscope, and with a very high resolution. This is actually CCD and a detector, how we can get the information from the sample in case of TEM. This is the sample, ultra thin sample. The electron beam is focus on this sample, and this is, as the sample is very thin, so the beam of electron, highly energetic electron, can pass through the samples. Moreover, these electrons are collected or concentrated on an objective lens which collect the electron at different points on the photographic films or on CCD. So from that, we magnifying that, we can get information from the sample, from the interior of the sample. If we compare the SEM and TEM with each other, so the electron beam in both cases, in case of TEM the electron beam is broad and static, but in case of SEM the beam is focused to a fixed fine points and the sample is scanned line by line. If we discuss the voltages, the voltage required for TEM is much higher than SEM, because we need the samples to be we need the electron beam to be highly energetic so that it can pass through the sample. In case of SEM, the accelerating voltages are much lower, not necessary to penetrate the sample, only need to scan the sample. And the interaction of electron with the sample process is very different from each other, because in case of TEM the sample should be thin so that the beam of electron can pass through it, but in case of SEM the wide range of specimens are allowed, and the sample preparation is comparatively very easy in case of SEM. So if you see the imaging process of both SEM and TEM, then in TEM electrons must pass through this sample, and we can get information from the transmitted beam of electron. But in case of SEM, information is needed to collected near the surface of the specimen, and the final point of difference between TEM and SEM is the image rendering. The transmitted electrons are collectively focused by the objective lens and magnified to create a real image, and then in case of SEM, beam is scanned along the surface of the sample to build up the image. So we have some advantages or merits and demerits of TEM as well. The merits of TEMs are that it has very high resolution compared to SEM, and its resolution is around 0.2 nanometer. The other merit is that it can have direct imaging of crystalline lattice, and we know the information about defects in the samples. No metallic strain coating needed. This is convenient for structural imaging of organic material. An electron diffraction technique is used to identify the phase, structure and symmetry determination, and the lattice parameters are also measured. Similarly, the disorder and defect are identified with the help of TEM. It has disadvantages or maybe sort of demerits as well, because the sample preparation for the TEM is comparatively difficult, because we need to make the samples very thin so that the electron beam can pass through it due to the conductivity or the elasticity or the sample thickness. So we have the applications of electrons. In the application of electrons, electronic microscope, we have TEM based 3D imaging. This is really very interesting 3D images, because we can get very beautiful or three-dimensional images of the material with the help of TEM. Here some of the images from the materials are present. You see we have a nano shapes 3D images from the samples. The environmental microscopy with TEM is possible. Here we can see the TEM, and we can get the information from the sample at very nanoscale. These are some of the images obtained from the TEM. This is actually the image of nickel catalyst film on a silica membrane, and this is actually the nickel oxide particle in nitrogen gas. And here we can see the resolution is as low as 0.20 nanometer. So this is really very high resolution, and we can see the atomic the lattice planes through it. So scanning transmission electron microscopy is another improvement in the field of microscopy, electron microscopy. This is actually the combination of scanning electron microscope and transmission electron microscope, and that can get very nice information about the sample. Here we have some of the STEM. This is actually called as scanning transmission electron microscopy. These are actually some of the images of STEM of 32 nanometer semiconductor devices with very high or good resolution, and this is actually giving us images in very in different colors. And this is actually the transistor structures, and this is the ADS sample of semiconductor devices obtained from this instrument. We have further development the focus ion beam that is also used to get information. This is also a part of electronic microscope. We can get the information about the crystalline material. Here we can see that a cross section of semiconductor that has been obtained from the sample. Here you can see this is the image of a wafer with a plasma FIB, and some other images of physical failure analysis. I mean, we can find out the cracks and the microstructure of the sample with the help of this system. Once we can find out the crack, we can find out the hardness and strength, and we can estimate some of the other mechanical properties of the samples. In application of electron microscope is really very vast, because we need this investigation of different parts of investigation of different instrument we use in our daily life. It is had vast spectrum of application, from aviations to mechanical engineering and medicine, as well as in all cases of research this microscopy is used. In the industrial application, here we can see that we have different we have really very nice improvement in the different type of cell phones, laptop, and the thing like that. So ICs are different type of automobiles. So this is only possible with the help of improving the performance of material. How we can improve the performance of materials? It needs to know the structure property relationship. The structure property, we know information about the structure of material with the help of electron microscopy. So once we can engineer the structure of the material, or we can change the atomic position, we can manipulate the properties of the material, and that is why we are getting some new material with high performance and good properties compared to the old one. And that is only possible with the electron microscopy. We have live applications of the microscopy in life sciences as well, because different type of viruses, and here we can see this is an image of the breast cancer cells, and sperm tangle up in a seminiferous table. So this is also some of the sample that are actually the biological samples, and the investigation of biological sample with the help of electronic microscope. So we can also get the information about the sample and improve the research in life sciences with the help of this microscopy. If we see the natural resources and energy, so the electron microscopies are equally important in this field, because as we discussed, we are improving the properties of the material, and this improvement in properties are only possible to make a relationship between the structure and property. Here we normally know that by changing the structure of material, the properties are changed. So investigating the structure from top to bottom approach are only possible with the help of microscopy and high resolution electron microscopy. Scientific research is also very much important, because uh, improvements are only possible when we perform the research and investigate new materials. Almost in all aspects of research, we need the investigation of the sample at microscopic level, and this investigation is only possible with the help of microscopy. So this further improves the importance of electron microscopy in our daily life and in scientific progress of the country as well. So here we can see that normally in labs, the electron microscopes are used to know the structure, phase, composition, lattice parameters, and the crystallinity of the samples, and these are some of the basic information what we need to know about the materials. So changing the structure can change the property, and we can get the information about the structure of the sample from this TEM. So this is something about it. So this is something about today lecture. I hope we can continue the lectures, and we can discuss some new topics in the upcoming lectures. Thank you very much.